Hi, I'm Sadiq Riazi and I'm going to talk about Microsoft Project HEAX. HEAX is a new hardware architecture for computing unencrypted data. Before jumping into secure computation, I wanted to point out to two key notions enabled by cryptography that we use on a daily basis. The first one is secure storage, which protects us from physical attacks. Anytime the data is going to be stored on the disk drive, it's encrypted, so that once it's stolen, it has no information about the original data to the attacker. We use this in Windows BitLocker. The second notion is secure communication, where any two people having a shared secret key can securely exchange data on an untrusted communication channel, such as internet. So how did the world look like before secure communication? We were using HTTP protocol to browse the web. Anytime we did a search, our search query and the results were directly revealed to anybody who wanted to intercept the message. And it wasn't until HTTPS that our query and results were protected. So what is secure computation? Going back to our original search example, not only we want to protect our query and results from anybody on the internet, but also we want to protect it from the server who is providing the answer to us. Not only this will be possible with secure computation, but there will be many amazing applications that seem impossible today. The first one is secure cloud computing, where companies can easily outsource their data and computation to a cloud provider without trusting that cloud provider. They can keep their data confidential. We can have technology companies to work on medical data without violating privacy laws such as HIPAA. We can have privacy-preserving face recognition. We can have personal genomics without surrendering our entire genome sequence to a company. So can all these amazing applications be possible? The answer is yes. We can use a new class of homomorphic encryption called fully homomorphic encryption, which was invented in 2009. So the question is, why don't we already have all these amazing applications? The answer is enormous computational overhead compared to plaintext regular execution. What is homomorphic encryption then? Homomorphic encryption is like any other encryption scheme, which has three main functionalities: key generation, encryption, and decryption. But it also has an evaluate function, and that's how we can compute unencrypted data. Like any other crypto systems, it's based on the hardness assumption of certain problem. Here, the problem is ring learning with error, which is secure even in the presence of quantum computers. In this problem, we work on polynomial rings over finite fields, which means we work with polynomials where the coefficients belong to a finite field, such as ZQ, integers modulo Q. And any operation that we do on these polynomials is modulo an irreducible polynomial phi of x. In the search version of this problem, given many polynomial pairs, bi's and ai's, we cannot recover the secret polynomial s. And this is the basis for all homomorphic encryption schemes based on RLWE. There are four main schemes, and the focus of this work is CKKS, which supports fixed point operations, which makes it a prime candidate for machine learning applications. There are two main paradigms: partially homomorphic encryption and fully homomorphic encryption. In fully homomorphic encryption, we can do any computation on encrypted data, while in partially homomorphic encryption, there are limited operations that we can compute. Homomorphic encryption is especially suited for secure cloud computing because it provides a secure storage as well as computation for data. Compared to other encryption schemes, it has relatively low communication but very high computational cost. And there is a question that can silicon help us to reduce this overhead? Here's a very short background on homomorphic encryption. We start with client's data, and we need to do an operation called encoding to map this data to a plain text polynomial. And we do encryption using public key to map this plain text to a ciphertext. Now the ciphertext is a pair of polynomials where each coefficient is much larger than plaintext coefficients. After we have this ciphertext, we send it to the cloud, where on the cloud we can do certain operations, addition, multiplication, and key switching, together with relinearization and rotation, which I'll talk about later. And then once the computation is finished, we send the data back, we decrypt and decode and have the plaintext results that we want. To categorize operations, on the client side, we have encryption and decryption, which are not computationally intensive, and we do not create customized hardware for it. On the server side, however, we have several operations that we need to accelerate. As we go from left to right, operations are more expensive. For ciphertext plaintext multiplication and ciphertext multiplication, we can unify them as an operation called dyadic multiplication. For the next three operations, which are called rescaling, relinearization, rotation, we can unify them as a single operation called key switching. One of the early solutions was proposed by Microsoft Research. The solution implemented the Yashi scheme, which is unfortunately not secure anymore due to subfield lattice attack. The next one, which is called HEAX Cloud, implements BFD scheme for specific security parameters. Here n is the size of the polynomial, which is 2 to the power 15. And q is log q is the number of bits that we have for each coefficient, which is more than 1,000 here. One homomorphic multiplication in this system takes around 27 seconds. And authors argue that most of the time is spent to put the data on off-chip memory and bring it back. Because these polynomials are very large, it's infeasible to store all of the intermediate polynomials on chip memory. The next work is focused on polynomial size of 2 to the power 12, and system can accelerate homomorphic operations by 13x. In this project in HEAX, we have two main design principles. The first one is that we do not want to be tied to any specific homomorphic encryption parameter, because these parameters are derived from the application that we want to target, and ideally we want to be flexible in that regard. The second design principle is that we do not want to be tied to any specific FPGA chip that we implement this architecture on, because we want to scale the design up or down based on the available resources. The design has 4 levels of pipelines, each with 10 to 100 stages. There are no prior implementation of CKKS scheme on any FPGA or GPU, and HEAX is the first architecture for this scheme. Comparing an operation called number theoretic transform, comparing HEAX for number theoretic transform to high-end GPUs, we get 36 to 80 times faster computation. Comparing homomorphic encryption operations, homomorphic evaluation operations, we get 160 to 260 times speed up compared to CPUs. In HEAX, we heavily rely on residue number system that I will talk about in the next slides. One of the main contributions of HEAX is a new architecture for NTT or number theoretic transform, for which the throughput can be adjusted, and we have a notion of a trade-off between resources that are consumed and the throughput of this module. We also introduce several techniques to reduce on-chip memory consumption. I will explain the design in a bottom-up fashion. I will start with level 1, and I'll talk about modular arithmetic cores. Then building on top of that, I will talk about number theoretic transform and how it's used in key switching at level 3. Level 4 is a system level where we have FPGA chip that is communicating with host CPU and also off-chip DRAM memory. In homomorphic encryption operations, we heavily rely on NTT, and the reason is that we need to do polynomial multiplication several times. If we do this naively, the complexity is O(n) squared, n being the size of the polynomial. However, if we transform these polynomials and do element-wise multiplication, the overall complexity would be n log n. and this is why we frequently transform polynomials. The idea behind a residue number system is that instead of operating on one big polynomial, we operate on many small ones. And the benefit is that we can pipeline all of these polynomials and get a huge performance improvement. Ciphertexts in homomorphic encryption scheme, in CKS scheme, are pair of polynomials where each coefficient is in ZQ. And this Q can be very big as 900 bits. So the idea here is that instead of operating on these big coefficients, we break them down into several parts. Here we can see that there are K parts. And we do parallel operations on these K different components, and at the end we merge the result. At level 1, we design 3 modular arithmetic cores, NTT, INTT, and Diadic. One of the big questions here is that what should be the word size and native operation here? Because Microsoft Seal uses 32 and 64-bit operations. But most of the Intel FPGAs that we have access to, they have 27-bit DSPs. We can realize these operations using these 27-bit DSPs, but that would be very inefficient. Instead, we ask the question that can we change the native operations to 27 or 54-bit operations? For this, we need to satisfy several constraints for each QI prime. One of them is that in number theoretic transform, these primes has to be congruent to 1 mod 2n. So we start with prime number theory, and that gives us a bound on how many primes we have for a specific bit width. And using Chebotarev's density theorem, we know what portions of those primes are congruent to 1 mod 2n. We can pre-compute all these primes, which is a one-time process, and change the native operation to 54 bits. Here are the schematic of these 3 cores. Now we can allocate as many cores as we want to adjust the throughput. However, in practice, to utilize these cores at all times, there is a huge machinery involved around them to provide right data at right time to these cores. Now I'll explain NTT architecture in more detail. Here you can see the access pattern within NTT, which resembles FFT butterfly structure. And on the left-hand side, you see the NTT module. So we start by allocating as many cores as we need, and we store the polynomial on BRAM, which is the unit of on-chip memory. We also store a couple of constant numbers, which are 2 polynomial constant numbers, which are used to accelerate the computation. As you can see, we need to fetch these coefficients to the computation and store them in the same location. In the next step, we need to fetch these 2 memory elements to the computation and store the result back. However, as we go from left to right, the access pattern changes, both in terms of which part of the memory we're accessing and how we are reordering the coefficients and doing the computation. At any stage, once 2 memory elements, which are referred to as these part of the polynomial, are fetched, we pass them to entity cores. After the computation is finished, we store them back into the memory. One of the limitations is that a unit of on-chip memory only allows us to fetch 1 coefficient at 1 cycle. If we need to fetch multiple coefficients at once, we need to store them in parallel VRAMs. The overall design has 90 stages. If we store coefficients naively on multiple parallel M20K, which are unit of on-chip memory, that would be very inefficient. We would only use 68% of VRAMs. However, as we discussed in the paper, we can compress this storage and get the VRAM utilization back to 98%. Let's look at NTT Internal Pipeline. In order to start the computation, we need to read these two memory elements. Once we read them, we can start the computation and store two memory elements back into the memory. If you continue doing this, you will see that there is a 50% bubble in the pipeline. In order to solve this problem and remove these bubbles, what we suggest to do is that we store twice the number of coefficients as before. Still, we need to do two reads, but this time we can do two independent computations, and we can write the result in two memory elements. If you continue doing this, you will see that the design is 2x faster because there is no bubble in the pipeline. Before starting the computation, we need to reorder coefficients because the access pattern changes in entity from one stage to another. For that, we need to instantiate multiplexers to select the right coefficient at right cycle and pass it to the input of the entity core. At the end, we also have to reorder the result back and put them in the memory. The naive usage of multiplexers, we would need multiplexers that select from 2NB. NB is the number of blocks in NTT for each entity input, which is very inefficient. However, we rely on the observation that for each entity input, for example, let's look at this one, there are a very limited number of possibilities that this input is selected from all possible coefficients. And we create optimal multiplexers to reduce the size of these multiplexers from 2NB to log 2NB, which in practice reduces the register utilization by around 4x. At level 3, we have KeySwitching Architecture, which here you can see the algorithm, and here you can see the architecture. In this design, we use all three possible cores, INTT cores, NTT cores, and Riazi. Each small square represents a computation core. One important notion here is that the relative throughput of these operations depend on homomorphic encryption parameter, and that's why we needed an NTT architecture for which the throughput can be adjusted. If you balance the throughput for the entire design, you would have a pipeline that looks like this, where all of the cores are being useful at all times. In order to reduce on-chip memory consumption, we need to align to synchronize these operations, and that causes two data dependency problems that we talk in the paper. At level 4, we have the system view, where all of the modules that we talked about are here on the FPGA chip, and we are communicating with off-chip DRAM, and here we are communicating with host CPU using PCI Express. In order to utilize these modules at all times, we need to interleave data transmission and computation. In practice, it means that we quadruple buffer the input and we have a double buffering for the output results. To reduce off-chip memory usage, we only store real linearization keys on off-chip DRAM, and we use all 4 DRAM channels in burst mode to match the throughput of this memory incoming data to on-chip memory with the computation that is happening on the FPGA chip. We implement HEAX on 2 different FPGA chips, ARIA10 and ASPLOS'20, for 3 different homomorphic encryption parameters, which are denoted as set A to set C. As you can see, for a single security parameter, we can scale the design by 2 times and have 2 times performance on ASPLOS'10. Comparing NTT throughput, we have 36 to 81 times faster computation compared to high-end GPUs. Comparing CKK's operations, HEAX is 160 to 260 times faster compared to CPUs. In conclusion, fully homomorphic encryption is a powerful cryptographic tool that enables computation on encrypted data. FHE is a prime candidate for secure cloud computing because it provides secure computation and storage at the same time. The work that we presented here is called HEAX, is a new hardware architecture for homomorphic encryption. And it's the first hardware architecture for CKKS scheme. Comparing two GPUs, we get 36 to 81 times faster performance. Compared to modern CPUs, we have 160 to 260 times faster improvement. Thank you for your attention.